Violet, we're going to get started here in a second.
All right. Thank you.
Didn't have meetings in the morning. Didn't have to drive 30 miles an hour behind an idiot. That would have been a little bit more prepared. Oops. Test. Valerie, you can hear me okay?
It's working.
All right.
Yep.
All right. If I can make it through this period, I'll make it through the rest of the day. So help me out. Readings. So I tried something different because if I tell you to read, you won't read. if I make it an assignment, then maybe you'll read. Unfortunately, when I made it an assignment, it also put a place in Canvas where you guys think you got to turn something in. Okay? Readings in the OWL system aren't scored per se. So I need to go through and just like go through and say, okay, this person read, this person didn't, and do that manually. That's not going to be automatic. Give me time, okay? I know it says 0 in Canvas. I haven't synced grades with Skyward. Your parents will never know. Okay? So if you're freaking out about that, stop. So I guess we'll just start with this. We're going to go through the worksheet, okay? And what we'll probably do is have you guys volunteer answers. Now, Violet, I'm going to call on you at least once since you're the only one here today from Zoom. If you got,
Okay.
if you've got friends at home that are not in Zoom that are in this class, there's not that many. Text them and say, hey, Mr. K is going to be really upset if you're not in on this thing. Okay. So we'll go through, I'm going to have you guys answering questions. I'll pick on you randomly. You better have an answer. You've had 2 weeks to do this. Okay. Or if you don't have an answer, you better have a question. And it's not going to be, I don't understand. All right. I need some connection there based on what you've read through, what you guys have looked at. You should have at least some kind of idea about how to approach it. Okay. And if you don't understand something, then you make sure you ask. Before we do that, is there anything that anybody would like clarification on in terms of the definitions and stuff that you've read about?
So for hydrogen bonding, it can only be present if it has it has bond an HO bond or
Yeah, so that's of all the things, hydrogen bonding tends to be the wonkiest in terms of understanding because of it has specific criteria. I need to find out where my boundaries are. Nope. Okay. All right. Okay, so hydrogen bonds. First off, they are not bonds. Okay. There's no sharing of electrons. Okay. All right. I told you guys I'd be honest with you at the beginning of the year. The most recent research within the last couple of years implies that there may be a little bit of electron sharing in there. That's beyond the scope of this class. Okay. So we're going to say that in hydrogen bonding, there's no sharing of electrons between molecules. Okay, so it's technically not a bond. The reason why they give it the name bond is because it is a really, really, really strong at a specific point. That's key. At a specific point, it's really, really strong compared to other intermolecular forces. It's extraordinarily weak when you compare it to an actual chemical bond. A bond that's holding a molecule together where you're sharing, the covalent or ionic bonding. Okay. So hydrogen bond, not a bond. And your criteria is that hydrogen must be covalently bonded to Hello? Yes.
Yeah, I spoke to the children yesterday, so we're aware of it. So you guys need to start digging now, or? Yeah. Okay, so it should be at,
Okay. All right, thank you very much, appreciate it. All right. Okay, so let's go to nitrogen, oxygen, or fluorine. So that's criteria 1. Any other atom that hydrogen is covalently bonded to will not allow it to be a hydrogen bond. Okay. Now, there's a second criteria, and that the hydrogen will be attracted to the another nitrogen, oxygen, or fluorine in the other molecule. Now, one of the keys there is that the oxygen, nitrogen, and fluorine in the other molecule, they don't need to be bonded to anything in particular. Okay. So if you've got 2 different molecules, for example, if I've got water, okay, the classic compound that has hydrogen bonding that occurs within it, I could have that molecule, of water attracted to another oxygen. Let's see here, what would be an oxygen compound in. Yeah. No. Wrong place. Where are my erasers? Okay. So we've met the criteria in that this hydrogen is bonded to an oxygen covalently. That makes the electronegativity difference between hydrogen and oxygen. Oxygen's got the second highest electronegativity. It's pulling the one electron that hydrogen has. It's pulling that electron away from it. not completely. But that one electron that hydrogen has is spending more of its time around the oxygen. What is a hydrogen atom made of? Come on, it's pretty basic. One proton, one electron. If that one electron is not spending its time around the proton, then what do we essentially have here? What's that? Just a proton. That's exactly what I was going to say, just a proton. That's what makes water special, okay? Water special in that you've got the hydrogen sharing its electron with the oxygen, that electron spending most of its time around that oxygen. And because that you have just a proton out here, no shielding, remember shielding effect with the electrons in different layers? It's just a bare proton, just like there. So it's going to be able to attract other things that are negative very strongly. In this molecule, the oxygen's more electronegative, so it's going to be partially negative. There, that attraction then can occur. And that's going to be a significantly stronger than other polar attractions, dipole-dipole forces.
So do only nitrogen, oxygen, fluorine work because they have a high electronegativity?
Exactly. That's why. Okay. They have to have that high electronegativity because that high electronegativity means that those atoms are pulling the electrons to them and they naturally are going to be more negative than what they should be. And the hydrogen is going to be much more positive than other atoms because it's just a proton, just like you said. Other questions before we get going?
What's the difference on the Lewis structure with the dipole and the induced dipole? What does it look like?
So we don't really, Lewis structure, we're only going to really show the polarity of the bond. We don't really show the polarity of the molecule. That you kind of have to look at the shape, how are the, what's the polarity of the bonds and stuff. So this molecule here is polar because the bonds are polar. The oxygens are going to be a little more negative. The sulfur is going to be a little more positive. The shape is bent, so we have an asymmetry there, okay? So we don't necessarily show the polarity of the molecule. That you kind of have to look at and see based on the other stuff. That's why what we did leading up to this is important in being able to just say, is this a polar molecule or not? Because if it's not a polar molecule, then there is only one way for those things to attract each other. Okay. Polar molecules, it's easy. It's just you got opposites attracting. Okay. You're gonna have the positive end and the negative end attracting each other. Everybody make how many, you don't have reds in their model kits. Let's do it with greens. So make a water. Don't put the lone pairs on the central atom. Oh, I just gave yours away. Where's one? Is there a box? Oh, there's one. Rick, Amon, that blue box there. Grab that for. Make 2 water molecules. Use greens for the hydrogens, just for something different. Hold them up as to how they would attract each other. Come on. Oh, wait a minute. You dance and sing. You don't catch stuff.
Yeah, I was gonna say play soccer, but that doesn't really help my case either.
Nope. See, that's not catching. That's not. Okay, so you see, that's like dancing though. It's like you kick stuff, right? You're either kicking the air or you're kicking the ball.
I guess.
Hold them up so I see what you're, okay. So you get the idea. Positive and negatives are going to track. I mean, that's, I think I had a lot of people freaking out that this was going to be hard. It's that simple. If you've got a polar molecule, so if you have water, so in this bottle of water, we just have a gazillion of those, right? 50, so 500 milliliters. Two, 5. So in this bottle, I have around 2 times 10 to the 25th molecules. So a gazillion, right? It's a liquid because those molecules are attracted to each other. They're not attracted to each other so strongly that they're stuck. They can move around, they can slide past each other. That's why it's a liquid. But if I take the lid off, it's going to stay a liquid for a really long time. It will evaporate eventually, okay, if I leave the lid off. But it's going to stay a liquid because of that attraction. So you just showed me. You got the hydrogen's going to attract the oxygen. So the hydrogen in one is going to attract the electron and the oxygen in the other. That's called a hydrogen bond. Why it's a liquid at room temperature. Okay, and we'll talk about states of matter and more in how those things are affected probably tomorrow. Okay. So what are the three types? What are the three main types? There's more than three, but what are the three main types of attractions? What's one? Dipole-dipole. Hydrogen bond is a type of dipole-dipole. It's just a special version. Okay. Dipole-dipole. Induced dipole-dipole, and that's going to be between a polar molecule and a non-polar molecule. Okay.
The dispersion.
Dispersion forces.
Yeah.
Those they're also called London dispersion forces. I abbreviate it as LDF. I think that may have been in one of the documents you read, or if not, just if you see LDF, that's what it means. Okay. Just like IMF is the Intermolecular Forces, not International Monetary Fund for those of you in business classes. Okay. Every time I read the news, I see the IMF, I say, what? Why? Why the intermolecular forces? Okay. Business people come into this class say, IMF, what? Why the International Monetary Fund? Okay, so so we've got polar and polar is dipole. Polar and nonpolar is dipole induced dipole. And nonpolar are London dispersion forces. Now, the thing about London dispersion forces, though, is that we can say two things about them. London dispersion forces are the only intermolecular force that can occur between nonpolar molecules. Only. But London dispersion forces can occur between any molecules, whether they're polar or not. The size of a molecule is also going to determine somewhat, actually not somewhat, is going to be a major factor in determining what type of force of attraction occurs between the molecules. If you have really large molecules, even if they have areas that are charged, and you could have a dipole-dipole force, if they're really large, it's entirely possible that the London dispersion forces could be greater in total than what the individual dipole-dipole forces are. Okay. Those are the three main ones. Now, what's another one? Alexa, say it again. Dipole ion or ion. And what's another one? No, that's just a dipole-dipole. So special version of it. What's another one?
Induced dipole induced.
That'd be London's dispersion forces. Yeah, so that's because if you have London dispersion forces are caused by the motion of electrons, and if you have two nonpolar molecules and one does that, that is the London dispersion force. It's going to force another molecule to rearrange its electrons as well. Okay. Alexa, you got so you said ion what? Okay, so you got half of it. What's of the last one? I think is the last one. Ion what? Ion dipole. So if you've got a molecule like water that has an area that's negative and areas that are positive, ions are positive and negative. There's going to be an interaction there, or can be. Now, how strong that is depends on how polar the material is. Okay. Best example of this is salt water. If you put salt in the water and stir it around, it's going to dissolve. That's because your charged ends of the hydrogen and oxygen ends of that molecule are going to be strongly attracted to the positive and negative ions that are in the salt. Okay. And that's what causes it to dissolve. If you try to take salt and dissolve it in, say, vinegar, not vinegar, oil, it's not going to dissolve. Okay. That's because the oil is nonpolar and won't attract those ions. Okay. I think that covers all the individual ones. So that was that first document that you read. Now pull up the worksheet. So the intermolecular forces worksheet. I think I might want to do this. Oh, there it is. That's my lap desk. I can't sit at a desk and grade papers. Can't slouch. Oops. This. Who wants to take the first question? Amanada. Correct. I mean, all you can do is look at the diagram, right? If you want to boil water, you don't end up with hydrogen and oxygen gas. That would be hazardous. Those two gases are kind of explosive when they're, next to each other with a hot flame. Okay. So if you're boiling water and all of a sudden you've got hydrogen and oxygen being given off, you're going to have trouble. When you boil water, you end up with water just in the gas phase. Okay. That's what the diagram was showing, right? All right, on average, are the intermolecular forces stronger in water as a liquid or water as a gas? Explain. I'm on? Okay, perfect. This goes straight to what we talked about at the beginning of the year. This is one of those things, it haunts you. It always keeps showing up. Remember that? And if V is negative, it's representing an attraction. If V is positive, it's representing repulsion. Again, we're not using that equation. That equation just lives and drives everything in the background. And Aman, you explained it perfectly there. The attractions in gaseous water are going to be less because your distance is greater. Remember, if you make this distance greater, this goes closer to zero, which means there's no attraction. Everybody okay with that? All right. Okay. This is where how we taught the previous unit with identifying polarity and stuff is a little bit different than what you're going to see in readings and stuff like that. Carbon and hydrogen do have very close electronegativities. What is it, like a difference of 0.3? I think hydrogen's 2.2 and carbon's 2.5. And many textbooks are going to say that's small enough that you don't have to worry about. And for the most part, yeah, that's true. Okay. If the electronegativity difference gets really, really small, we don't look at too much that contributing to the polarity of a molecule. I'm not saying it's zero. That's what I was going. So when I taught you guys about polarity of molecules, I was thinking zero polarity versus some. So even though hydrogen and carbon are close together, and even though they're saying the electronegativity of carbon and hydrogen are roughly the same, okay, what they're implying there is that it doesn't matter a whole lot, which is true, because if you look at and compare with oxygen, that's a huge difference. Even with carbon, it's a difference in electronegativity of 1, and that's getting pretty big. Okay. So recall that the electronegativity of carbon and hydrogen are roughly the same, but that oxygen has a significantly higher electronegativity for each of the type of compounds, alkane, ketone, and alcohol, predict whether or not the compound is expected to be polar or not. Now, I know this is going to be a little bit challenging here, but if you were to look at those formulas, okay, so these are alkanes, right? These are ketones, these are alcohols. Their formulas give you some idea. In fact, we talked about alcohols when we did our Lewis structures, right? We said that alcohols, they end in this OH. So in that molecule right there, you're going to have blah, 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 oxygen, hydrogen. And what do we have available right now? What has to be available? No. Hydrogen, all this is compounds, so we got a bond there. You can have a hydrogen bond. That's key. So if I have just a bunch of those molecules and all of them have that, then all of them have hydrogen bonding that can occur. Right? Look at these alkanes. Polar or nonpolar? Just looking at them, polar or nonpolar? Come on. Why? Okay, electronegativity is low, but okay, I want everybody to make propane. Make it. You get the model kits, make it. Use black atoms for the carbons, white atoms for the hydrogens, and you don't need to necessarily draw it. This is kind of telling you how to put them together. Remember, carbons all get together in string. So attach all 3 black atoms with sticks in a row. And where there's a hole in them left, just put hydrogens. Sorry, Violet, you're gonna have to just, you can look at my molecule.
All right.
Unless you got a molecule kit at home. Pull up. Once you got them done. So this is propane. This is what's in the tanks that they sell at the gas stations to hook up to your gas grill. When you light it, it combusts with oxygen in the air to produce what? Come on. A CH compound plus O2 is going to give you what? Every single time. Carbon dioxide and water. Okay. So this is propane. Is this polar? When you look at it, so if we used what I taught you guys with polarities, the arrows would all be pointing into the carbons. I know that they just said that the electronegativities are small. They didn't say zero, okay? So if there is any imbalance, all of these hydrogens are positives. Is there any way that you can have, is there any way to have opposite charges on the exterior of this atom or this molecule? No. This is a non-polar molecule. If you look, the reason why I'm not going to have you make the rest of them is because all of those ones they have listed there as alkanes, they would just get longer. Okay. You'd add a fourth. So in the next one down, butane. That's what's in your lighters. For those of you who smoke, stop. It's bad for you. Okay. So your butane would have a fourth carbon just in a string like this. And you just go, if you're looking at it like this, you know how I said they're in a straight line? Well, that's in your Lewis structure. On this, they're up and down. Okay. That's the shape of that molecule. But it's just be extending this thing out, continuing to be nonpolar. Okay. Make acetone. And all you need to do to make acetone is take off the two atoms that are on the center, the middle carbon, and double bond another, use a different color. So blue or yellow. You guys have yellow, right? Yeah. I don't have either blue or yellow, so we use my red one. Got a molecule that looks like that now, right? Polar or not? Polar, because the oxygen, that's negative, right? And we said these hydrogens are going to be positive, at least slightly. Definitely polar. We got this negative up here sticking out like a sore thumb, and we got all the positive area down here. Every single one of these ketones is going to be polar. What kind of intermolecular forces then can occur between these? So if I had a bunch of these, so if everybody threw those into a bucket, and we said, pretended that they were, actual molecules, what kind of attraction would we have between them? What's that? Explain how. Criteria number one. Where are those hydrogens bonded to? Carbon. Is that on your list? So it can't be a hydrogen bond. Okay. But it can be a what? If they're polar, dipole. So that's why you got to be careful with the use of that hydrogen bond, because you may have, so even though we got an oxygen here, it's not going to be a hydrogen bond occur between these because we don't have hydrogen bonded directly to that oxygen. You got to have the hydrogen bonded directly to it for there to be a hydrogen bond, a possible hydrogen bond. Okay. So the alcohol, let's go ahead and do it. Propanol. Go ahead and put those two hydrogens back onto that middle carbon, and then put an oxygen and then a hydrogen on one of the ends. Doesn't matter which end. You're gonna have this. This is where we got to expand our horizons a little bit. This isn't just as easy as just can you hold the molecule in one hand thing, okay? In looking at this molecule, do we have an area of negative that is kind of distinct or sticks out a little bit versus the others? And the answer is yeah, that. Okay, that's going to be very negative because that's the oxygen. We got a hydrogen attached to it. Joey, what kind of attraction can we have between these? Because we have the hydrogen bonded directly to the oxygen, that hydrogen now can attract another one. Okay, Ainsley, toss me your molecule. You can overheat it if you want. Okay. So I can have then, if this molecule here, this is the oxygen, this is the hydrogen, this is my oxygen and hydrogen, there's an attraction right there. A pretty strong one. Because that's going to be a hydrogen bond where you got the very positive hydrogen and the very negative oxygen attracting each other. Okay. Can you catch? You're a singer though. See? All right. Everybody okay? You can give her some lessons on catching, like catching football. Okay. All right. So we kind of answered 3. Now things are going to start falling into place a little bit more. So for each type of compound below, indicate how the boiling point changes as the molecular weight of the compound increases. All you got to do is look at the table, right, Dylan? They all increase. It does not matter. If you increase the mass of the molecule, it is going to be a greater molecular, greater boiling point, which kind of leads into the next one. Based on your answer. Okay, based on your answer. How do the intermolecular forces between molecules change as the molecular weight increases? Somebody who hasn't answered one here yet. Ainsley? Well, so the intermolecular forces are going to increase with increased molecular weight. I'm sorry, yeah. Intermolecular forces are going to increase with increased molecular weight. Here's why. Ready? More electrons. So London dispersion forces occur between everything. Okay? Everything, whether it's polar or non-polar, London dispersion forces are always going to be a factor. In water, very minor. The fact that in water, we have the hydrogen bond occurring, it's going to, that hydrogen bond that occurs between water molecules, it's much more important than the London dispersion force. Okay. But overall, London dispersion forces increase with increased mass because you simply have more electrons. If you have more electrons, you have a bigger electron cloud. If you have a bigger electron cloud, you have more ability for that thing to move around and have different areas that are positive and negative instead of being completely equal all around. That's just because of the randomness of their motion. Remember, the electrons are constantly moving, randomly moving around. That means that at some point in time, they're going to be bunched up in one area versus another. that doesn't last long, okay? It's not a long-lasting thing. But for that moment, you have, that's why it's called a temporary dipole, okay? For that moment, you have an area that's going to be positive and an area that's going to be negative. And if the molecule is large enough, you could have multiples of those. It's going to go away, but for that moment, you have an area where things can attract. Okay. The larger the molecule gets, the more electrons you get, the stronger that force is going to be because you have multiples of them. All right, for an alkane, a ketone, and an alcohol, with roughly the same molecular weight. This is important because we know that the molecular weight's different than the intermolecular forces are going to be different because of the London dispersion force. But if they have the same or similar molecular weight, now we can look at the different types of intermolecular forces. Okay. Somebody give me 3 compounds that were within 5, because it didn't matter. You just need to find 3 or that were within 5 grams per mole. You already answered. You answered the easiest. All right, go ahead.
Pentane.
Boiling point. Just go ahead and give it to.
56 degrees Celsius.
All right. Butanone.
Yeah.
It's not butanone. It's butanone.
79. Wait. Just kidding. Just one of the ones that I need more.
Those are the masses.
No, those are the boiling points. I just wrote it wrong.
Okay, so 79.6.
Yeah.
And what's the third one?
Never mind. I was looking at the molecular weight at the boiling point. So I have they have the same, roughly the same molecular weight, but not the same boiling point.
Okay, is there one that had, is there an acetone is close to 36, like up to 41 or down to 31?
Oh, look at the molecular weight.
Yeah, and just tell me what the boiling point is.
Oh, okay, sorry.
So butanone,
Then 59.6. And then butanol,
is butanol.
117.
Okay. We determined that pentane is what, polar or non? Butanone is butanol is even though these two are polar, what's different? Alexa. We have to be careful. Okay. Butanol has a boiling point of 117. Is there a nonpolar alkane that has a boiling point greater than butanol's 117? Yeah. So one of the misconceptions that students get a lot of times, because we focus on saying that the hydrogen bond is so strong, I want to emphasize, really emphasize that a hydrogen bond is really strong at one single point where that attraction is occurring. Okay. London dispersion forces may be at one individual point very weak compared to a hydrogen bond. But if you get a whole bunch of them together, they will be stronger collectively than the individual hydrogen bond that occurs between two molecules. That's why you can have molecules that are nonpolar that have extraordinarily high boiling points. Okay. Great example in the kitchen. Your oils that you cook with. Does anybody work fast food in here? Oh, good. Try not ever to. I worked at Wendy's for a summer. It's miserable. You smell like grease and you can never get it out of you. Okay. You've seen them deep fry the fries though, right? You guys may have a deep fryer at home. That deep fryer's temperature gets upwards around 400 to 500 degrees Celsius. Now, when the fries or whatever it is you're deep frying are not in it, that oil is not boiling. It's just sitting there hot. Okay. May smoke a little bit. Okay. But your oils are nonpolar. They can exist at that extraordinarily high temperature because of the London dispersion forces that are occurring between those molecules. Okay. All right. Repeat 6 with another 2 more sets of compounds using grammatically correct English sentences. Describe any general pattern. Okay, we did that. Do we really need to break them? Is it pretty clear? Okay. Does anybody have any questions? Are you doing okay so far based on the answers you had before? Nods or shakes? Okay. Yeah,
So are the ketones in the middle just because they're polar, but they don't have oxygen on?
exactly.
So it's not.
So think of it like, so if you have a polar molecule, you have an area that's permanently charged. And that permanence is what makes it stronger than the London dispersion forces, because as I've described, the London dispersion forces is not one area that's always going to be positive or negative. They're constantly changing. And that's what makes it weak. It's not the fact that there's no polarity. It's just that the polarity is changing constantly. And it's not very polar to begin with when that happens. Okay. Someone give us a statement for 9. Based on the data in table 1, does the presence of a dipole moment in a molecule tend to increase, decrease, increase, or decrease the strength of intermolecular forces? Explain your reason. Someone's give us a statement. Joey? Okay. Having that dipole moment. Kind of goes with that, what we're talking about with the permanency of it. Okay. Is the strength of intermolecular forces determined by the bond strengths within the individual molecules. So number 10, we've been focused on the exterior. Does the intermolecular force, like the polarity of the molecule, is that driven by how strong the chemical bonds are within the molecule? Draw water because it's quick and easy. So we know that water molecules attract other water molecules very strongly. Is that determined by how strong the bond is between hydrogen and oxygen? That's what the question's asking. No. The strength of the force of attraction between molecules is based on that, the difference in electronegativities and how those are arranged. Now, how strong is the chemical bond within the molecule? Okay. Yes.
So it's like the double bonds in ketone, does that really matter? Like, does that contribute to anything?
The thing it contributes to is the shape. Okay, which, as you know, as we saw, you know, if you change, I'm going to put this back together. The fact that I've got these two atoms here, if I replace that with a doubly bonded oxygen, it doesn't change our model significantly. What I will tell you is that what these models don't do a great job of is showing how that angle would change. But the thing is, we still are going to have this. This is contributing to the shape. And in combination with what its electronegativity is what's making it polar. Okay. So the other one had a shape similar, except the atoms that were here were the same as all these and nonpolar. So it's a combination. If I had an oxygen singly bonded here, okay, I'm not, this technically this really doesn't, well, this wouldn't exist long. It would be fairly reactive, okay? But even if I had just that, that would still be polar. Not necessarily as polar as the other one with it double bonded, because it's not as distinct. But it's that electronegativity along with the shape that's giving it. That could be a double bond, doesn't matter. Okay. Okay, I want to hear what you guys have, what one of you guys has to say. So number 11, what is the difference between intramolecular forces and intermolecular forces? Joey? I'm going to change the last part, between molecules, okay? So intra, the prefix intra means within. Inter means between, okay? So when we're talking about an intramolecular force, We didn't call it that, but covalent bonds are intramolecular forces. They are forces of attraction inside the molecule. Intramolecular forces are the forces of attraction between molecules. Okay. Rank these intramolecular forces. No, I don't want to rate that. Rank them. I need to go check something here. All right, what do we rank them? One being the weakest, one being the weakest, up to the highest being, was it 1, 2, 3 being the highest? You already answered enough, Joey. Let's get somebody else. Let's get Stone. Let's get somebody else. One.
Induced dipole, induced dipole, that's the weakest.
Okay. Second
Dipole, dipole,
and the third.
A bond.
Now, their term here for induced dipole, that's our abundant dispersion force. Okay, so if you want to make a note of that someplace on there, just to make sure things are clear. Okay, so let's go a little bit quicker now. 13A. Just people who haven't answered.
Induced dipole, induced dipole.
Okay. What? So if that's the only one, that's got to be the strongest, right? Okay. Number 14. Hope, give it a shot. Yep. Are there any others? Let's go with the London dispersion forces or just dispersion force. I understand that in this worksheet they introduced it as induced dipole, induced dipole. I want you to switch gears into calling it dispersion forces or London dispersion. So you're right. So we would have two types, because remember what I said, every molecule, no matter what, has London dispersion forces, because London dispersion forces are caused by electrons, and everything has electrons. So now, Hope, you got to answer part B. So we've got dipole, dipole, and London dispersion. Which is the strongest of the two? The dipole, dipole. This is where that comparison that we did here with the list that Aminata gave us, where we've identified those things that are polar and non-polar. I know the focus on that question was the molecular weight to begin with, but you can see that if you've got the same molecular weights, that you've got differences in those boiling points because of the attractions. All right, alcohols. Who's got number 15? Come on.
Hydrogen bond and dispersion forces.
Okay. I'm fine with that. If you listed all three and it said hydrogen bonding, dipole, dipole, and dispersion forces, I'm fine. Keep in mind, hydrogen bonding is just a type of dipole, dipole. Okay. And what's the strongest force present? Okay. Now, I do want to go back to something I said earlier. Because if you, let's go look at the decane, 2-decanone and 1-decanol. Those are the ones that have the most carbon. So if you go back up to that graph and you look at the decs, okay, decane, 2-decanone, and decanol, we can see that the differences in their boiling points are not as drastic. They're still there, but they're not as drastic as before. And that's because our London dispersion forces, because the molecules are getting bigger and bigger and bigger, the London dispersion forces become more important, more important, more important. Oh.
So you listed the dispersion force with dipole? Like if it was a dipole and a,
Oh, which one's the most important?
no, like instead of saying induced dipole and dipole,
Oh, just say dispersion force.
okay, dispersion force,
Mhm.
and dipole and dispersion.
Just dispersion force. I just kind of gave the answer to number 16. So in terms of intermolecular forces, why does the boiling point increase? And what's happening? Well, what type? There's more dispersion forces. So the larger the molecule is, the more dispersion forces you have. All right. So you may have any questions on these answers, because this kind of gets it all, right? These are our intermolecular forces. These are the things that affect how strongly molecules attract each other. If you can identify whether a molecule is polar or not, or if you're told whether a molecule is polar or not, we look at the different factors. Is it polar or not? If it's polar, what are we going to look for to help decide even more? Hydrogen bond. Remember, hydrogen bonding's got a very narrow, okay, very narrow set of criteria that you must meet for that to be a possibility. Okay. Questions? Oh, crap. Where's mine? All right. I'm going to leave it at this for today. You have owls. They're due 14th and 17th for you guys, right? Start working. That way I'm here. You can ask questions if you're having difficulty. Okay. Now, the one set of owls that is, it's more tutorial type stuff, I would make sure you get, that's the ones due on the 14th, right? It's the introductory, it says Unit 7 introductory, do those. Okay. Hopefully in combination with what you've read, worksheet you've done, what we talked about today in class, those should be relatively easy, okay? But go through them. Give some more details of what we talked about. I know I've got people that have completed both sets. If you're in that category, I would ask you, are there any questions that you have that would help clarify stuff that you did? All right. I'll go the in the analysis the not really thing. So, but in the regular part of the owl, I'm like, what's that? Scores and stuff. It tells you. It doesn't give you a score. It just tells you time score. So I can look at. Viola, are you still there?
Yes. you're welcome to kick out if you want.
Awesome.
And then if you are, I'm going to go ahead and end this. If you're going to stay, I'll leave it on. If you got a question, holler. So what are you
All
going to
right.
do?
Thank you. Bye.
All right. Bye-bye. Thanks.